Hi team, we're going to do a little video today where we're going to do a sample problem around a heating curve. These things could also be called a cooling curve. So in the innards of my graph here, what we have going on is I have some material that's being heated. I like to mentally think about this as perhaps I have some substance that's sitting on a hot plate. So I'm just continually adding energy at kind of a constant rate of time here. So I'm adding heat. And what's going to happen, of course, is my material is going to start to go up in temperature, or I'm going to have some phase changes. So the way that this works is when something is actually heating, that's when we would be climbing on the vertical axis here. And so I would have this curve right here. And then when something is horizontal, what we're doing is we're putting all of our heat energy into a phase change. And so we're causing the material to go through that physical change. In this particular case, I'm showing all 5 possible regions of something like melting an ice cube. So I would have an ice cube down here that is potentially at some very low temperature. That would be lower than 0 degrees Celsius. So I don't know, whatever you want to call it, minus 20 degrees. I throw that thing onto a hot plate and imagine that it's a very kind of cooperative system where we're going to say that this magical hot plate is able to increase the temperature of the block uniformly without yet melting anything. So it's a little bit of an assumption on how this would all work, but this is how the math works, the theory behind these curves. So all of my energy is going into increasing the temperature. Then when I reach the melting point, which of course for ice is 0 degrees Celsius, then I'm going to put all of my energy into the melting process. Now that I have entirely liquid water, I would be again heating that liquid water with my energy. And then this would be vaporization. And you can literally grab a portion of this. Let's say that I was looking at a region of my heating curve here that's 20% of the way in. That would mean I have vaporized 20% of my material. 80% of it would still be in the liquid form at the boiling point. So here's me boiling. It's almost all gone. Here it's all gas, and my magical hot plate is able to continue heating the gas. All right, when we want to do mathematics with a curve like this, the first thing I would like you to get accustomed to is ask yourself, am I dealing with a region of the curve that has a temperature change? If you do, then you're going to invoke Q equals MCAT. You're going to use the temperature change here. This is going to be the specific heat capacity of that material. Be aware that the specific heat capacity of an ice cube, of the solid, is different than that of the liquid, which is different than that of the gas. So we have to be really cautious that we're getting the right specific heat capacity for the right phase of the material. And then I have my mass, and here's that heat going in. If you do not have a temperature change, then we're going to use one of these two equations. These are very similar. Q, still a heat, still measured in joules. And then what I would do is I would multiply something called the enthalpy of fusion, is the phase change for that melting process or the freezing process. Okay, and this is the amount of energy it takes per gram of material to do that phase change. And then I would need to multiply it by the mass of the material so that I could figure out what's the total energy for, say, a hunk here. I forgot to put a little m up there, so forgive me. Okay, alternatively, you could go to the old Google machine and you could look up delta H, or the enthalpy of vaporization. So that's the phase change that takes me from the liquid to the gas, or that would take me from the gas to the liquid in condensation. Those two values, depending on the direction you're going, it is simply a minus sign. Okay, so let's see what a problem would look like for us. I'm going to kind of keep these things handy so that we can see our equations. Here's a sample problem I would like us to do. In this problem, I say how much energy is needed to heat a block of ice from negative 15.0 degrees Celsius, so way down here somewhere. We're going to melt it, the whole thing, and then we're going to heat that remaining water up to 25 degrees Celsius. The block of ice is 2.40 kilograms. And then these are pieces of information that are properties of water that I would have to look up. Here's the specific heat capacity of ice, right there. Here's the specific heat capacity of liquid water, right there. This is the enthalpy of fusion. This is the amount of energy, 333 joules per gram of ice. All right, the beauty of how this works is we're gonna figure out how much heat energy, basically from here to here, is associated with the heating part of the solid. Then we're gonna do a separate calculation and figure out how much heat energy is associated from here to here to do the phase change. Then we're gonna do a third calculation where we're gonna figure out how much heat is involved from here to about a quarter of the way through. I'm thinking about the 0 degrees to 100 degrees is the range for liquid water. And so I'd be maybe making my way up to about here or so on that particular heating curve. So let's go ahead and do our calculation. All right, my first segment here, I'm going to say Q is equal to mc delta T, but I have to pull the correct numbers. What is the mass? The mass is right here, 2.40 kilograms, but be aware that I need my unit agreement, so I'm going to need to do the unit conversion on this to ensure that I'm actually in the correct units here. And so I'm going to convert my kilograms to grams. We could see how to do that elsewhere. I'm going to just go ahead and move 3 decimal places, and I'm going to keep track that I have 3 sig figs here. So here's my first number. It's going to be 2,400 grams of water. Then I'm going to plug in my specific heat capacity. We're doing the ice first. So I'm going to do the 2.09 joule per gram per degree Celsius. And then I need to do my delta T, my temperature change. Always final minus initial. I'm going to use my common knowledge about water that the final temperature of this ice cube, of the solid form, the final is going to be 0 degrees Celsius, and that's when it's going to start melting. So I would have 0 degrees Celsius here, minus final minus initial, but my initial carries a minus sign of its own, so I have a minus minus there, 15 degrees C. Okay, let's go ahead and just grab that number while we're sitting on it right now. 2,400 times 2.09 times 15.0. I had another sig fig. I don't think I have room to write it in there. I have my 3 sig figs there. I'm going to assume that that's not going to limit my sig figs. Okay, so when I do this calculation out, I get 75240 joules. Okay, degree C cancels that guy. Gram cancels gram. I'm left in joules. And this was going to have 3 sig figs. Okay, out to the 10th place. So 3 sig figs, 3 sig figs. And remember, this guy actually has 3 sig figs. So I'm good there. Okay, my second Q. This is going to be this spot right up here. So now I'm looking at the phase change. This is going to be, I'm going to do my mass first. Okay, so I'm going to first go my mass in grams, and then I'm going to multiply by the enthalpy of fusion here. And so this is going to be 2,400 grams multiplied by 333 joules per gram. 333 times 2,400, 799. And then that is going to be 1, 2, 3 quality sig figs also. Okay, my last Q, maybe I'll call this 1, 2, and 3, is going to be this little segment up here, another Q equal MCAP. First my mass again, 2,400 gram. Okay, now I need my liquid. I'm in the liquid phase by this point because I've melted everything. 4.18 joule per gram per degree Celsius times delta T. Final minus initial. Here's my final. 25.0 degrees Celsius minus initial. Again, I know that it was 0 degrees Celsius. And I'm going to assume that's 0.0. All right, this one's going to be 25. 250,800. Good to 3 sig figs. Now I'm ready to add these numbers together. So my final answer is going to be 1, 0.125. All right. So here's my final answer. Remember, it is possible to gain significant figures when you're doing the addition process, and it looks like that happened to us. Alternatively, I could say this is 1.125 E6 joules. And there's my final answer. I want to say one quick note about the theory of these things. You should never, ever, ever have a situation where these Q's have different signs when you're adding them up. If you're going in this direction and you're adding energy, you're going to have positive Q's across the board. If you were doing a cooling curve, you were having energy leave your system, every single one of these Q's is going to be a negative sign or have a negative sign. So you need to just be aware of that and pay attention, and your final answer would also be a negative if you were cooling the material. All right, hopefully that helped. Have a good one.